Nir Mandelker. I'm a graduate student at the Hebrew University working with Avishai Dekel, about to enter my final year. It's my great pleasure to discuss with you today essentially a continuation of the talk we just heard by Yicheng Guo discussing some of the properties of these high-redshift clumps in the simulations. And then I'll continue in the second part of my talk discussing more new insights about violent disk instability in general. This is done with a great many collaborators. Of course, Avishai Dekel, and I really have to thank Frederic Bourneau for having to drive his daughter to the airport, thus essentially doubling my talk time. So that's the sign of a true collaborator. So I really appreciate it. And oh, good, this is working. Okay, so what is it we know about clumpy disks? Well, we've heard a lot of talks about the high-redshift disk, about clumps in general, just sort of great talk by Yicheng, but still I would say the only thing we know for sure about clumpy disks is that they exist and that they are absolutely robust. You can't get away from them in both the simulations and in the observations. There's been an enormous amount of observational work studying these clumpy disks at high redshift. These are just two examples by a sample by Bruce Elmegren, clump cluster and chain galaxies. And when you simulate these extremely high redshift disks with the high gas fractions, which has been shown in these papers, you basically reproduce the observations quite well. And these are two of our simulations run by Daniel Severino, and they quite robustly match the observations, and there simply doesn't seem to be any way around them in the simulations that we're looking at. What do we think we know about clumpy disks? Well, we think that these high gas fractions in these high redshift disks cause giant clumps to form in situ in the disk through violent disk instabilities, and we think that it has to do with the Toomey-Q parameter, but wait until the end of my talk. However, we also think that clumpy disks might be merging systems. Well, we're not sure about that. We think that clumps should survive stellar feedback and live long enough to migrate toward the center, contribute to the growth of a bulge. We also think that clumps should disrupt and not survive feedback. So we think we know a lot of confusing things. What would we like to know about clumpy disks ideally? Well, we would love to know, as Yicheng just told us, what is the fraction of clumpy disks as a function of disk mass, as a function of galaxy redshift. How many of these clumps were formed in situ in the disk through some form of instability? What fraction of them join the disk as mergers? Which of these clumps should survive stellar feedback? Which of these clumps should not? And what are the various properties of these clumps? So in these two papers, one from last year and one that I'm currently working on, I basically discuss all of these questions. In the talk, I'm going to be focusing on these last two in terms of the effect of feedback on clumps. Now, in order to do that, my main tool, and I took this slide from Joel Premack. I expect he'll probably show it again in his talk tomorrow. My main tool for this work is 3 generations of hydrodynamic simulations using the ART code run by Daniel Severino, essentially focusing on what we're calling Gen 2 and Gen 3, which are the Vela simulations. These are a set of about 30 simulations with on the order of 25 parsec resolution, run using the same exact initial conditions, once using only supernova feedback and once using non-thermal feedback from young stars, the radiation pressure of young stars. We heard a bit about those simulations over the last couple of days. They span, in terms of the virial mass at Z of 1, between 10 to the 11 and 10 to the 12. And well, these are the simulations I'm going to be looking at. Now, you might ask, why is it so complicated to know, do the clumps survive the feedback or not? Well, this is an old paper by now from 2010 using what we call the generation 1 simulations of the Hydro R, slightly lower spatial resolution with only supernova feedback, but you can actually trace quite nicely the formation and the evolution of a clump as it migrates and works its way toward the center of the disk. A couple of years later, Shai Ganel, using the Gadget 2 simulations with essentially strong winds put in following the Oppenheimer and the Vey model, found that when he implements this strong wind feedback, the clumps that did survive now don't. So there was a big argument here, what should clumps survive due to feedback? So to answer this question, I'm going to be comparing the 2 generations of simulations with weak feedback and with strong feedback, and trying to see the differences. So first of all, proof by pretty pictures is the most convincing. So these are my pretty pictures. This is the run with only supernova feedback. This is including the stronger feedback. You can see that the gas disk expands, the bulge shrinks, giant clumps survive, and small clumps disrupt. This is, by the way, the same galaxy at the same snapshot, comparable number of clumps. Another example where most of the clumps are a bit smaller will show you that indeed a lot of the smaller clumps do indeed disrupt in the stronger feedback simulations. I'm going to want to quantify this effect in just a moment. But if a picture is worth 1,000 words and a movie is worth 1,000 pictures, and that's a lot of words, so I'm going to show you a movie from one of our simulations run with RP. This is a face-on map of gas and a face-on map of young stars. This is stars younger than 100 million years. And what you're going to see as this runs, you're going to see a sequence of minor mergers, trigger compaction event, or blue nugget formation, as we heard a lot about yesterday, which then leads to an extended VDI disk with long-lived clumps that will migrate toward the center. So let's basically take a look at this. So this is the first of the minor mergers. This one doesn't cause any too dramatic effect, but in a moment, another two mergers will come in, triggering the compaction event, and then the clumpy disk is going to form straight after. So there's the merger, driving a lot of gas into the center. You can see the formation of a blue nugget. And now you're going to see a very large extended gaseous disk forming around the central nugget, and you're going to see lots of clumps form, and they'll survive, and you can see them essentially migrating toward the center. There they are. And these clumps are long-lived, just in the picture that we painted, that I painted based on the Generation 1 simulations. I'm sorry, the movie's a bit choppy. So I want to analyze these clumps, and to analyze these clumps, I have a 3D clump finder. I identify clumps both in the gaseous component as well as in the stellar component working in 3D, and I combine the sample of clumps to study their properties. I don't want to go into the details about it, about how the clump finder works. You can talk to me later. This particular analysis is not going to be using the very short time steps that I used to make the movie, but this particular analysis is going to be using snapshots that are separated by about 100, 150 million years. For the time being. So, all right, study the effect of feedback on clumps. Let's look at the mass function of clumps. Well, in blue you see the simulations without, with only supernova feedback. In red you see with the stronger feedback. This is clump mass. This is clump mass. It's normalized to the disk mass. Clump star formation rate. Clump star formation rate normalized to the disk mass. And this is really weird because they're identical. Where's the feedback? All right, well, to answer the question, where's the feedback and why these are identical, let's put all the clumps that I found on the plane of the clump size versus clump mass. Now, the red lines are lines of constant volume density. The cyan lines are lines of constant surface density. And in color, I have basically a shape parameter for the clumps, where clumps up here are very oblate and clumps down here are very elongated, very prolate. What you can immediately see is that in the simulations with stronger feedback, the clumps become a lot less dense. There are a lot fewer very dense clumps, and there are a lot fewer oblate clumps. The clumps become more elongated and less dense. Now, I can plot on the same plane the lifetime of clumps. If I want to see which are the clumps that survive and which are the clumps that form and immediately disrupt. So clumps up here are the ones that survive. Clumps down here are the ones that disrupt. And you can see that many more clumps in the weak feedback simulations are going to be long-lived. A lot fewer of the clumps in the stronger feedback simulations. In fact, the only clumps that survive are clumps that are dense and are oblate. That's how they resist tides and shear within the disk. But they also have to be massive, above about 10 to the 8. And they have to be massive in order to withstand the feedback. Incidentally, if I plot on the same plane the star formation rate contribution from the clumps to the disk, there doesn't really seem to be that much of a difference between the two feedback scenarios, since there's just going to be a big burst of star formation, which will then wind up destroying the clump in the stronger feedback simulations. But that will not affect the total contribution of star formation of clumps to the disk star formation rate. When I take that into account, and this time let's only look at the dense clumps, which we expect to survive, you indeed see that you suppress dense clump formation with the stronger feedback simulations above about 10 to the 8 solar masses, which is where the feedback clumps at lower masses are going to be disrupted by feedback, and you can see the similar effect in the star formation rate. So there's the feedback, and this is what it's doing. If I'm now ignoring the weak feedback simulations, I'm going to only be focusing on the stronger feedback simulations, the ones with radiation pressure, and I want to examine how the distribution of clump masses and star formation rates varies with redshift. That's what I have here. Every color here is a different redshift bin. This is the clump mass in gas plus stars. This is clump mass, again, normalized to the disk mass. Star formation rate and star formation rate, which is normalized to the disk total. And what you can see is that the clumps seem to become more massive at later times. But when you normalize the mass to the disk mass, as is expected from the standard tumor instability, all the plots basically line up. And there's no real evolution. They all basically break off here at about the 2 scale. At the high mass end, the slope of the mass function is somewhere between minus 1.7 and minus 2, which is very similar to the talk we saw in the first session about the mass function of globular clusters in the local universe. And there's presumably an underlying connection here. Star formation rate as well, if you examine the absolute value, it appears to change with redshift, but as soon as you normalize it to the disk value, the high star formation rate and all collapse, and they all have exactly the same function. The gradients, we heard Yi Cheng talk about gradients, so what do we see in the simulations? The plot that Yi Cheng showed was actually from the old simulations, from the Generation 1 simulations, but not much has changed in the Generation 3. If I focus on the massive clumps that I expect to survive, you still see a strong gradient in the clump age, no real gradient in the clump star formation rate, and I'll get back to that in just a moment. The difference might be if I look in the baryonic mass of clumps. In the old simulations, we saw a very strong mass gradient. In the new simulations, we don't really see anything because the inflows of fresh gas from the surrounding gaseous disk onto the clumps is balanced by outflows due to feedback and also gas being stripped due to tidal effects. However, if I look at the stellar mass, which is what Yi Cheng is observing, I do see a gradient. And I do see a gradient because the clumps are continuously forming stars throughout their lifetime. Now, I don't have time to talk about it here, but you can come up to me later, and all this can be quite nicely modeled in a bathtub-type model for the evolution in the lifetime of a clump. I'm not going to go into that. How much time do I have left? Oh, beautiful. Oh, I'm sorry. This is, so just to end this point, this is what we saw from Yi Cheng a moment ago. This is observed gradients, and these are observed gradients by Natasha Forster-Schreiber. This is, again, very similar to what is predicted in the simulations and does seem to hint at, as we've been saying, that the massive clumps do survive stellar feedback, and they're able to get all the way back to the bulge. So this is just to summarize this first part of the talk having to do with the properties of clumps. Violent disk instability due to intense gas flow and high gas density. In situ giant clumps and transient features form in the disk. We also have ex situ clumps that merge. I didn't actually talk about ex situ clumps in this talk, but you can tell they're about, in terms of the total number of clumps, about 15% of them are not formed in situ. They are ex situ mergers that join the disk from the outside, although they make up about half the mass because they're in general much more massive. In situ clumps are younger, they have higher specific star formation rates, and they have bluer colors. They have lower mass and metallicity than ex situ clumps. And while about half the galaxies are clumpy, in total about 30% of the star formation rates in the clumps, which is in broad agreement with observations, and the gradients in age and color due to migration and accretion from the disk, and the mass gradient is a little iffy. Now, since Frederic was so kind to give me so much longer, I have the great pleasure to tell you about some work in progress, which we think is extremely interesting, and will be the subject of 2 upcoming papers, and has to do with what is causing the violent disk instability in the first place. So Avishai showed this picture in his talk, and I like it. It's one of my favorites because it shows a very nice clumpy disk, but it shows that this disk is far from being the nice, thin, axisymmetric structure that Toomre had in mind when he formulated his original criterion. This thing is a total mess. Now, while clump formation or violent disk instability in general is really typically associated with tumor instability driven by high gas surface densities in the high redshift universe, giving you low Q, driving you down to 1, we see that in the simulations, this doesn't seem to work. We try to measure tumor Q in the simulations in regions that are continuously forming clumps, and we systematically get Q to be about somewhere between 2 to 5. Now, I'm not going to talk a lot about this because Shigeki Inoue tomorrow morning is going to give you all the details about this. This is the work that he's been leading. I am going to show this, which I just love so much. What we've done is we've highlighted here a region that's about to form a clump. You'll see in the next few time steps that a clump here is going to form. This is a map of Q, and you can see here that in this region that's about to form a clump, Q is above 3. As I take it forward in time, this region collapses, eventually forming a clump, although it started from a very high Q initial condition. Now, in the collapsed clump, sure, Q is extremely low, but that's because the collapsed clump is totally nonlinear with extremely high surface density, so that doesn't really mean much. And we do see this in a very systematic way. In all the disks that are continuously forming clumps, we see time and time again that new clumps are being formed in regions with extremely high Q. So how can this be? What is causing the instability if it's not the standard Q equals 1 instability? Well, there are a few ideas that are in the literature. Bruce Elmergreen had a nice paper a few years ago discussing the rapid decay of turbulence. That might push Q up to about 2 or 3. You could talk about irregular rotation or counter rotating streams, but the idea that we have in mind that I want to focus on over the next couple of minutes is compressive modes of turbulence. Now, what do I mean by that? So this is just a cartoon. Just imagine a random velocity field. And let's look at this little region here in the center, which I've zoomed in on here. This is the mean velocity within this region, so it's the constant vector field. This is the linear term in the full velocity field, and this is the nonlinear residual. So the full velocity field is given by the constant, or the mean, the linear term, and the nonlinear residual, which is going to be very small. This linear term can be divided into several different components. It can be divided into compression and expansion, which is going to capture the same divergence as the full field, but it has essentially zero curl. It can be divided into a part symbolizing rotation, which has the same curl as the whole field, but it has zero divergence. And it can be divided into shear. Shear is going to have no divergence and also no curl. And the sum of these three comprise the linear term in the velocity dispersion. Now, the compression and expansion is often just called the compressive mode of turbulence. The rotation and the shear are very often lumped together in something called the solenoidal mode of turbulence. Now, these two terms are going to tend to stabilize a region against collapse. This term, well, not if it's going, not when the hours are going out, but when the hours are coming in, this is actually going to give you an instability. Now, you can quite simply show, if just by an equipartition argument, that if the turbulence is isotropic, you expect the solenoidal mode to have twice the power as the compressive mode. And you can think of that just because the solenoidal mode is a two-dimensional motion, the compressive mode is a one-dimensional motion. So in equipartition, you get twice the power in the solenoidal mode. Q has sigma up on top. So if for some reason the compressive mode of turbulence is going to dominate, then high sigma will give you high Q, but you're not going to be stable, because high compressive modes of sigma are going to induce you to become unstable. Now, this was shown very nicely in a paper about a year ago by Florent Renaud and Frédéric Bourneau. They looked at a merger simulation of the antennae galaxy, and what they found was right around closest approach, the gas mass fraction that was undergoing compressive tidal forces increased. That caused the energy in the compressive turbulence to become higher than the energy in the solenoidal part of turbulence, which is contrary to what you expect in equilibrium, and that caused a boost in the star formation rate. So we wanted to see, well, can we explain VDI in these high Q regions by similar effect? So what I'm showing you here is just 4 snapshots at the same redshift from 4 of our simulations. Now, this is just one snapshot, but you'll have to take my word for it. These two galaxies are clumpy for most, if not all, of their history. These two galaxies are stable for most, if not all, of their history. And if we try and look at what the different modes of turbulence are doing here, now, please don't take this with a grain of salt. Take this with a whole salt shaker. because I'm still working on this, and this is very preliminary, and I'm not sure I would trust the quantitative exact value of these plots, but still I find it incredibly striking that my first attempt worked so nicely. If you look at the ratio of the solenoidal energy to the compressive energy, for the two non-clumpy cases, it fluctuates about the value of 2, and for the two clumpy cases, it fluctuates around the value of 1. Now, I don't know exactly 2 or exactly 1, but the point is, compressive modes seem to be more important for these two simulations than they do for these two simulations. Now, again, please, whole salt shaker, I'll get back to you on this soon. Open questions that I would like to answer. What causes the compressive modes to dominate in the first place? Do compressive modes induce the clumpy disks? Do the clumpy disks induce the compressive modes? Which is the chicken, which is the egg? And eventually, what would be super interesting is if we could come to a modification to the two-way Q, where the sigma here should really only be the solenoidal component. And if we use this, do we get confirmation only in regions where Q is indeed 1? And I'll end there. Thank you.
So Yuval couldn't be here, but I'll ask this in his stead. Okay. Magnetic fields. I'm sorry, but I mean, the whole second part, magnetic fields are obviously going to play a huge role in anything that's going on there.
Yes.
So your thoughts?
I remember a talk that you gave not long ago where someone asked you about magnetic fields, and you said, yes, this is true. I can't say much about it at this time. Yeah, it's a good point.
So, yeah, I'm going to talk about magnetic field tomorrow, so you'll know. I have a question regarding the feedback. So, obviously, feedback is very complicated, and we all have our favorite models. But one traditional game that people are playing is to calibrate the feedback to the M star M halo relation, to the abundance matching relation. Okay, I'm not saying it justifies that your feedback model is the right one, but it gives an indication whether the overall galaxy integrated strength of feedback is the right one. And so since, Shai-Genel feedback results in the clump destruction and the feedback you used in the art simulation doesn't, how does the feedback model with respect to the M star halo relation?
So that's a good question. In a paper by Chris Moody, and a bunch of us were also on it about a year ago, he compared M star M halo in these two generations of simulations. The model with supernova with the non-thermal radiation pressure does bring us a lot closer to the M star M halo relation than we previously were. It's still off by about maybe like 50% or so. We're not perfect. We're still forming slightly too many stars at high redshift, and we have slightly too low gas fractions at low redshift. But within a factor of about 1.5 or so, we do match all the observational constraints. And so as we've heard in previous talks, these simulations are capturing a lot of other very robust phenomena about the evolution of high redshift galaxies, and we interpret this as saying that qualitatively all the phenomena are the same. They just perhaps happen at slightly higher Z when the gas fractions on simulations are slightly higher and compared to the redshift 2 observed gas fractions. But we are very close. To within 50% we're on the relation. That's the short answer.
We don't calibrate it just using the star 99 is telling us our stellar evolution and the typical numbers of the ice. No correlation.
So Nia,
that the radiation field is coming from the right amount of ionising photons, and the ionising photons are being trapped in the region of the thick.
You're making the same mistake as you're not properly modeling ionising pressure. So what does that mean?
Are we after the discussion?
So Nia, I'm slightly disturbed because, okay, so your last part of the talk, you find from your simulations that in contrast to the simple-minded Q about one picture, you find Q equals 2, and then you throw your explanation, when you throw your general explanation overboard. What about reality? The reality is we are finding Q less than 1, and we are finding that as you go from low to high redshift, you know, the dispersions change roughly like in the tumor picture. So I'm a little disturbed that you so easily throw away reality.
It's a fair question. Wait, let me. I'm sorry, my computer died. I have to get a new battery, so I can't show you the plot. Even in our simulations, in the nonlinear collapse clumps, in the regions that have already undergone collapse, Q is indeed very low. Q is indeed 1 or lower. So this is true, and this is what is observed. You observe the clumpy disks, and you observe the clumps, and you see Q is less than 1 in and around the clumps, and this is true. We agree with that. We see that in our simulations as well. But what we're doing is we do two things, and so again, Shigeki will talk more about this tomorrow. We smooth out the disks to get back to the pre-collapse conditions, trying to mimic the linear regime. That's one. And two, we take the simulation to go back in time to before the clump formed and ask what is Q in the region that is about to collapse into clumps. And we see that there, Q is indeed high. Over to it can be 5 or sometimes even more. So that's what motivated us to look into this other things. Avishai has something to say.
You say the right thing, but I want to add to it. We don't ignore reality at all. And there is an open issue here, which is very interesting. However, both observations have errors and simulations have errors of different kinds. So until the dust settles, we should play the game and try to understand how the simulations explain the observation. Now, Nir's point was exactly the issue here that we have to pay attention to. It's very hard to apply the tumor analysis or test it with a real galaxy that is nonlinear, because tumor Q is a linear concept. But when we face the galaxies in the observations and the simulations, we have a nonlinear system. So how do we, it's a big problem. Now, if you just apply tumor analysis, you find both in the simulations and observation, I'm just repeating what Nir was saying, Q is below 1 in the clump regions. Okay? But it's almost meaningless. So that's where the simulations help. Okay? Because we can play this game that you cannot play. We go back in time. We have a time machine. And we take the clump and you follow it to its proto-clump region. And we know here maybe tumor analysis may be valid. Let's try it. Surprise. Q is 3, not 1. That's where we are. Now let's try to learn more. I don't know the answer.
Okay, I think this is a good place.
Run by Daniel Severino, and they quite robustly match the observations, and there simply doesn't seem to be any way around them in the simulations that we're looking at. What do we think we know about clumpy disks? Well, we think that these high gas fractions in these high redshift disks cause giant clumps to form in situ in the disk through violent disk instabilities, and we think that it has to do with the tumor Q parameter, but wait until the end of my talk. However, we also think that clumpy disks might be merging systems. Well, we're not sure about that. We think that clumps should survive stellar feedback and live long enough to migrate toward the center, contribute to the growth of a bulge. We also think that clumps should disrupt and not survive feedback. So we think we know a lot of confusing things. What would we like to know about clumpy disks ideally? Well, we would love to know, as Yicheng just told us, what is the fraction? Nir Mandelker. I'm a graduate student at the Hebrew University working with Avishai Dekel, about to enter my final year. It's my great pleasure to discuss with you today essentially a continuation of the talk we just heard by Yicheng Guo discussing some of the properties of these high redshift clumps in the simulations. And then I'll continue in the second part of my talk, discussing more new insights about violent disk instability in general. This is done with a great many collaborators. Of course, Avishai Dekel, and I really have to thank Frédéric Bourneau for having to drive his daughter to the airport, thus essentially doubling my talk time. So that's the sign of a true collaborator. So I really appreciate it. And oh, good, this is working. Okay, so what is it we know about clumpy disks? Well, we've heard a lot of talks about the high-redshift disk, about clumps in general. Just sort of great talk by Yicheng, but still, I would say the only thing we know for sure about clumpy disks is that they exist and that they are absolutely robust. You can't get away from them in both the simulations and in the observations. There's been an enormous amount of observational work studying these clumpy disks at high redshift. These are just two examples sampled by Bruce Elmer-Green, clump cluster and chain galaxies. And when you simulate these extremely high redshift disks with the high gas fractions, which has been shown in these papers, you basically reproduce the observations quite well. And these are two of our simulations using the ART code run by Daniel Severino, essentially focusing on what we're calling Gen 2 and Gen 3, which are the Vela simulations. These are a set of about 30 simulations with on the order of 25 parsec resolution, run using the same exact initial conditions, once using only supernova feedback and once using non-thermal feedback from young stars, the radiation pressure of young stars. We heard a bit about those simulations over the last couple of days. They span, in terms of the virial mass at Z of 1, between 10 to the 11 and 10 to the 12. And well, these are the simulations I'm going to be looking at. Now, you might ask, why is it so complicated to notion of clumpy disks as a function of disk mass, as a function of galaxy redshift? How many of these clumps were formed in situ in the disk through some form of instability? What fraction of them join the disk as mergers? Which of these clumps should survive stellar feedback? Which of these clumps should not? And what are the various properties of these clumps? So in these two papers, one from last year and one that I'm currently working on, I basically discuss all of these questions. In the talk, I'm going to be focusing on these last two in terms of the effect of feedback on clumps. Now, in order to do that, my main tool, and I took this slide from Joel Premack. I expect he'll probably show it again in his talk tomorrow. My main tool for this work is 3 generations of hydrodynamic simulation